So this chapter called Supplement A is about solving systems of equations, which is a revisit of a topic we would have addressed last year in your Algebra 2 class. So hopefully, if this doesn't look too unfamiliar, so we're going to start by discussing several different ways that we can solve these systems of linear equations. So the first technique we're going to talk about is graphing. So we'll start by defining what we mean by a system of linear equations. Okay, so a system of two linear equations is basically two equations that are linear. When we say linear, what do we mean, really? We mean that the exponents on the variables are 1, and the only operations involved are addition, subtraction, multiplication. So in this case, x and y are variables, and a, b, c, d, e, and f are all like real number constants. Okay, so what is a solution then to a system? So we say that a solution is going to be some xy that just satisfies both equations. So for example, if I have the system 4x plus y equals 8, and then 2x minus 3y equals 18, a solution for this system could be the point 3, negative 4. And the reason I know that is because when I plug in 3 for x and negative 4 for y, the first equation is satisfied. And I do the same thing in the second equation, that's also satisfied. Now, the question that probably remains is, okay, I see that 3, -4 is a solution, but how would we find something like that? Well, one answer is to graph that, or graph this system and look for the intersection. So what I'm going to do is I'm going to start by writing these systems, or writing each equation, the system, in slope-intercept form. So that means getting the y part by itself. We okay there? And then I'm going to make a XY table for each of these. So if I'm going to do this by hand, I would prefer to kind of pick these numbers, these x's, so that they're relatively far apart. Let's see. So maybe I get 0 and 8, and then maybe I'll do 4 and -8. Again, it doesn't really matter how I'm picking these, but I would like to pick them so that they're kind of far apart, so it's a little bit easier to, when I draw my graph, to find that intersection. And then maybe here I'll do 6, and that comes out to be -2. And so then it's time to go ahead and draw my graph. Right. So let's see. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So this graph I'm going to draw in red, and this one I'll draw in blue. So let's see, I have 0, 8, and then 4, -8. Oops. And then I have 0, -6, and then 6, -2. So there's my solution, which is the intersection of the two. So the x value there appears to be 3, and the y value there appears to be -4. We all okay with that? What's the drawback to this method if we're doing this by hand? Neatness counts here, right? Counts quite a bit. If you don't do a good job drawing your graph, it's going to be very tough to get the correct intersection. In addition, would I really be able to tell from my hand drawing the difference between if my answer is like 3, -3.9 and 3, -4? Probably not, right? So we'd prefer not to have to do this by hand, but rather do this electronically. So what I would do now is I'm going to use my calculator. So again, I'm going to type these into my calculator, my equations have to be in this slope-intercept form. So I'm going to do negative 4x plus 8 into one slot, and then 2/3 x minus 6 into the other slot. I'm going to just double check my window to make sure it's something reasonable. This seems reasonable, especially since I know what the graph already looks like. Probably for most of the problems, that -10 to +10, that standard window would be okay. So I'll hit graph. And as long as I can see my intersection on my screen, my graph is good enough. It doesn't have to look exactly like mine. As long as you can see the two lines crossing, your picture is good enough. Now to have the calculator find that intersection, we're going to press second and the trace button. Select the intersect command. Now the calculator is going to ask 3 questions here, but it doesn't really matter the points we pick for our answers as long as we've only graphing 2 lines. Since we are only ever going to be graphing 2 lines, I'm just going to press enter 3 times. And there it says at the bottom, the intersection is at x equals 3 and y equals -4.
So we can do this method instead of the hand drawing one?
Yes. In fact, we'd prefer to do that because the hand drawing one has a lot of problems. If you have like a decimal point in an answer, all of a sudden that becomes really difficult to kind of suss out by hand. So yes, we would like to be doing that. Now, okay, so an answer can look like an intersection, right? Does every answer to a system just can be represented by one intersection like that? Well, no. Now, of course, we have the situation where we get exactly one solution as we saw in our previous example. But 2 other things could happen. We could get infinitely many solutions. I abbreviate that situation as IMS because it's a whole lot of letters to write. And we can have no solution. And again, I'm going to abbreviate that NS because, again, a lot of letters potentially having to write. So when we have exactly one solution, that's one intersection that we're looking at on the graph. When I have infinitely many solutions, I have my 2 lines overlap. So basically, on my calculator, it just looks like there's one line there. And then no solutions is, what does that look like? That looks like parallel lines. Everybody okay there? So let's look at a couple more examples to see some of these other solution types. So if we wanted to type this into our calculator, we'd start by putting it into slope-intercept form. So I'm going to just take each equation and get the y part by itself. And this can sometimes be the worst part, what we're doing right here. Notice that I'm not going to bother with reducing the fractions. Again, you could do that if you wanted to, but since we're just going to type this into the calculator and find an intersection or whatever, we don't need to do that. So we'll go back to the y equals and we'll type in our two equations. Does everybody feel okay with what we're doing here? Yeah, nothing too terribly complicated, right? We're just using our calculator. Okay, I'll go ahead and graph down and take a look at what's going on.
So cool. Do we need to have like certain graph settings?
If you just use the standard window, -10 to +10, it's probably going to be okay for most of these problems.
Okay.
As long as you can see the intersection,
Then we're good.
you're good.
All right.
Now in this case, I only see one line, right? Now it's two possible things are happening here. Either the two lines are overlapping, or the other line is just off the screen somewhere and I can't see it. Everybody agree with that? So the easiest way to check is if I take a look at, say, the y-intercept here. I'm just going to check to see if I get the same number when I plug 0 in for x. And if I get the same number in both equations, then I know they're overlapping. And if they're different numbers, then, well, it's probably the line just is off the screen. And I'd have to do some adjusting on the window. So when I put 0 in for x, I get -8/3. And when I put 0 in for x, I get -16/6. But really, that's the same number, right? Everybody agree? And it doesn't really matter which x value I pick to check with. I just picked 0 because, well, I can plug x equals 0 into it and just do it in my head, you know? But you could have picked 100 or 10,000 or whatever. It doesn't really matter. Hi, Ashley. Now, I want to point out to you, if we had bothered to reduce that equation, you'd have noticed that they are identical equations, right? Which would, again, without even having to graph anything, that would imply that you have infinitely many solutions. So in all reality, you could have done this without even graphing it at all. Everybody's okay with that idea? And really, if it's me, I could tell here without even having to rearrange anything that this is infinitely many solutions. And the way I could tell
That's a nice little hack.
is that the coefficients from one equation are just 2 times the coefficients in the other equation. And as long as that multiplicative, that factor, is the same for all the coefficients, it's infinitely many solutions. So you don't even have to really rearrange it if you just notice that right from the get-go. But either of those 3 ways of doing this is fine, right? If you go through and you rearrange everything and you look at the graph and it's like, oh, there's one equation or one line, okay. Or if you rearrange, you notice, hey, it's simplified down to the same equation, infinitely many. Or if you just start at the beginning and look and say, oh, look, these coefficients are just the factor of, are all a factor of this. So it's infinitely many that way. Any of those approaches are valid. They're fine. They work every single time. Let's look at another example here. So again, I would start by just taking each equation and rearranging things. So that you are in slope-intercept form. That means really just getting the y by itself. Now, right away, I can tell that this isn't an infinitely many solution situation, since the two equations are different, right? So, okay, well, let's go ahead and just type it into our graph and see what we get picture-wise. So negative 2x plus 4, and then negative 2x plus 1. Take a look at my graph. So there's one line. There's the second line. Now I notice that these two lines are not intersecting, and really even better than that, what do they also look like they are? Parallel. So one of two things is happening. Either they're parallel or the intersection is just somewhere off the screen. Again, what I would do is go back and take a look at my equations here. When I look at my two equations, I notice that the slope is the same. And I know that lines with the same slope but different y-intercepts are parallel. Everybody okay there? Or, even better, again, for me, I can look at the original pair of equations and tell that this is no solution. So I can see that the x and y's are the same factor, but the other constant is not. So if the x and y's are the same factor, but the other, what it equals to is not the same factor, then again, I know that this is no solution. And I can do that without having to draw anything or rearrange anything. I can just take a look at what I have. Again, any of those three approaches are fine. They all are accomplishing the same thing. It's a level of comfort. The trickiest part about these is noticing that it's happening, right? Because most of the time we're just rearranging to graph, but occasionally you get one of these that when you graph it, So, Mr. Kulik, is this as hard as this section gets? Well, no. The hardest thing we'll do in this section is we can do the same kind of problem as a story problem. So let's take a look at this situation. Uh-oh.
Like same concept, but now we have to do it from storage.
Yeah. Okay. So it says here you ride an express bus from town center to your street. You have two payment options. Option A is to buy that monthly pass and pay $1 per ride. Option B is to pay $2.50 per ride. The monthly pass costs $30. Our question is, how many times do we have to ride the bus before those total costs will be the same? So I would start by defining my two variables. So what are the two variables going on here? What are the two quantities that can be changing?
Option A and option B.
No, option A and option B are fixed,
Oh,
right? We've defined clearly what those two options are. Describe again what we're trying to figure out. Just in your own words. What do we have to know to answer the question? Not quite. Okay, so how many rides? So the number of rides is something that can change, right? So I'm going to use that as one of my variables. Okay. And depending on how many rides we take of the bus, what else has got to change? Yes, Ellie. Yeah, so I'll call that the total costs to ride the bus. Everybody agree that those are kind of the two quantities that are going to be changing? The number of times we ride the bus and how much it costs us to do so. Right? Okay. Now I'm going to write an equation. Not surprisingly, I'm going to have one equation for option A and one equation for option B. Everybody's okay with that idea, I hope, right? Seemed clear that hopefully that the two equations are going to come from option A and option B. Okay, so option A, again, what does option A say?
monthly pass is pay $1 per ride.
Okay. So how is the total cost going to be related to that?
$30.
Well, the total costs are going to equal the monthly pass. Maybe I'll write in words first. And the word "and" is going to mean what operation? Addition. So I'll just write a plus sign. And then $1 per ride. Everybody's okay with just writing this in words? Okay. Our total costs, we said we're going to be the letter T. The monthly pass cost $30. That was told it to us in the problem. And then we have $1 per the number of rides, so just 1R. Everybody feel okay how we decoded that into an equation? Okay. What does option B say? Okay. So total costs equal $250 per ride. So the total cost was T, and the number of rides is R. So T is just 2.5R. Everybody okay there? So my system then that I'm going to solve, actually, let's do that, is that. So just go to my calculator. Now here, almost certainly I'm going to have to change my window, right? So I'm going to use X to represent R and Y to represent T. What's that one doing back there? Okay, what are we doing here? Oh my goodness. All right, hold on. Okay. There we go. All right, so let's reset our window here. Because clearly we know that the number of rides can never be negative. Everybody agree with that? So the X will start at 0. Now, I don't know how many rides I'm going to have to make to have these two things even out, but I would assume that like probably less than 30, because there's 30 days in a month. If I ride the bus once a day, that seems like a reasonable upper bound to pick. Everybody okay with that reasoning? Now let's look at the total costs. So again, can't have negative costs to ride the bus. They're not going to pay me money not to ride it. So let's put that lower bound at 0. And now let's think about the upper. If I rode the bus 30 times and it cost me $2.50 each crack there, what's that turn out to be, like $75 or something? Feel like that's a reasonable upper bound? Since clearly this will be cheaper if you rode the bus 30 times using option 1, it'd be $60. So somewhere in there, 75 seems like a good upper bound. And again, I'm just kind of guessing. It doesn't really matter too much as long as I can see the intersection. So there's option A and there's option B. So this spot right here, the intersection, is what I care about because that's when the two plans cost the same amount. Everybody agree with that? Because they have the same y coordinate right there. Okay. So I'll pick that second trace command and then pick intersect. And again, as long as I just have two equations, I can just press enter 3 times. So it says the intersection is at 2050. So at 20 rides, the plans cost the same. Is everybody okay there? So again, the actual solving part, once we had our equations written, was really easy, right? Nothing to it. The hardest part was decoding that paragraph into the two equations and then having enough sense to think about the context to pick a decent window so you could find the intersection. If we had used the standard 10 to 10 window, we wouldn't have seen the intersection. But anytime you're dealing with a story problem like that, we really do need to take a moment and think about the context involved. Okay. But that's probably as bad as things will get here in the first section. Any questions so far? This all seem familiar? We did this in first semester last year, but it's been some time. But this tends to be one of the stickier topics, because I think this is at least lightly an Algebra 1 topic as well. Okay, looking at section 2, we're going to look at graphing systems of linear inequalities. So again, if I have a system of linear inequalities, that means that the linear part means the exponents on the variables are both 1, and the only operations going on are addition, subtraction, multiplication. And the fact that it's an inequality means that instead of equal signs, we have less thans, greater thans, less than or equal to's, or greater than or equal to's. Now, a solution is a little bit different here for linear inequalities. We should probably, instead of saying and, we should say all. Okay, so what does this mean? So if I take my first equation and I plug my point in, I get 4 is less than or equal to 5. So that's true. And if I plug into the second equation, I get 4 is greater than 1. That's true. So 0, 4 is a solution. But if I were actually to graph these two things, Note that 0, 4 is not actually a point on either of these two lines. Right? So if I just graph the line y equals 2x plus 5 and the line y equals negative x plus 1, notice that the point 0, 4 isn't actually a point on either of them. And that's because the way we graph an inequality and the way we graph a line are different. Okay? So let's talk about how we graph an inequality. So the first thing we're going to want to do is rearrange our equation so that it's in slope-intercept form. Remember, though, that if we multiply or divide by a negative, we flip the inequality. So then we're going to draw our line as if the inequality was an equation, but we use a dashed line for greater than or less than, and a solid line for greater than or equal to or less than or equal to. Then we're going to shade above your line for greater than or equal to or greater thans, and below your line for less than or equal to or less thans. Keep in mind that this could mean, when we say above and below, in the case you have a vertical line, this would now turn into to the left and to the right. Right? Above turns into the right for a vertical line, and below turns into left for a vertical line. So let's do an example of just graphing a single inequality, just so that we can play around with this a little bit. So here's my inequality. First thing I want to do is rearrange this so that I get, actually I'm going to make that a 6. I'm going to rearrange this so I can get it into slope-intercept form. So I'll subtract over the 4x. Notice that adding and subtracting from both sides doesn't flip our inequality. And then I'll divide by -2. That, though, does flip our inequality. So then I'm going to pretend that I just have an equation and use that to graph my line. So maybe I'll use the point 0, and when I plug 0 in for x, I get -3. And then maybe I'll use the point, I don't know, 3 when I plug that in. 2 times 3 is 6, and -3 then is 3. Again, there's nothing magic about the 2 points I chose. I just chose 2 points. It was all kind of arbitrary. Okay. 1, 2, 3, 1, 2, 3, 1, 2, 3. So 0, 3, and then 3, 3. Now, because it was a strict less than, I'm going to draw this with a dashed line. Everybody okay there? And then I'm going to shade below. So what does below mean? So like I pick a point and kind of draw it down. That's basically the side of the line I'm shading on. So I'm shading over here. Everybody okay with that? Let's do this. So what that means is any point that I pick in this shaded region would satisfy that inequality. Right? So maybe this is the point 4, -5 or something. If I plug that in, 4 times 4 minus 2 times -5 is greater than 6. So 16 plus 10 greater than 6? Absolutely. So this is just as an aside. Right? The graph was already done. I was just trying to explain what this really was representing. Grace? I just was saying any point in the shaded area, for example, the point 4, -5, should satisfy my inequality. You're welcome. That's just, you can use that to check to make sure you've shaded the right side, the correct side. Does that feel okay?
Yeah.
Yeah, no problem. Sometimes I get going a little fast and it's tough to, you know. So what does that mean for the, if we're graphing a system of these inequalities then? So if we're graphing a system of these inequalities, what we're looking for then are the points that satisfy both inequalities. Or graphically, what we're looking for is like the overlap in those shaded regions for each inequality. So we'll do a couple examples here, and then we'll be donezo for today. Sound good? Okay. So again, we'll start by just generating a graph as if the inequality was an equation. And again, there's nothing special about the x and y's that I chose there. I just chose some stuff that would be convenient to graph. I'm going to graph this first one in blue and the second one in green. 2, 3, 4, 5. 1, 2, 3. 1, 2, 3. 1, 2, 3. All right, so 0, -5, and then -3, 1. And because this one had a greater than, I'm going to draw that one with a dashed line. And because it's greater than, I'm going to be shading above. In my other one, I have 0, 3, and then -3, 0. Because that was a less than or equal to, this one gets the solid line. And because it's less than or equal to, I'm going to be shading below. So my solution really becomes that section there that is the overlap of the two inequalities. Leo?
I don't understand how you say that, like when you choose your points, like, they don't really matter.
Because any 2 points on a line will generate the straight line. So I'm just picking an x and finding the corresponding y. It doesn't really matter what I pick for x. I'm just picking something that was convenient to do the arithmetic with. Is that what you're asking?
Yeah.
I can't just choose anything for x and anything for y, but I'm choosing the x, plugging it in, getting the y. I'm just choosing x's that it's trivial for me to plug it in my head. You know what I mean? So when you're drawing your picture, if you wanted to only draw this piece, that's the overlap, that's good. That would be preferred. If you want to draw both sections, try to do it in a way that it's easy for me as the reader to tell. So if you did, something like this, where it's easy to tell the overlap because it's gridded or whatever. Just try to be conscientious about how you're doing that shading so that it's easy to tell where the overlap is for the person that's me grading your work. You know what I mean? Okay. Here's a quick question. Does every system of inequalities have to have a solution? Right? Does not. Should be fairly easy to come up with a situation where it doesn't. So let's say that you had parallel lines, and the blue one we shaded above, and the green one we shaded below, and there's no overlap at all. So you can have no solutions. Now, technically, all of these problems are infinitely many solution problems because in one of these shaded regions, there's infinitely many points. But you can still have a strict no solution situation if you have parallel lines and you're shading opposite ends. Let's do one more. Example, and then we'll call her quits. Okay. So again, I'm going to start by noticing that middle inequality is not in slope-intercept form. So I'd want to start by rearranging that one. Oops. Let's make that negative. Okay. And now I'm going to think of each one of these inequalities as an equation. So when I have something like x equals -3 and there's no y spot, what does that mean? Well, this is describing a vertical line. If x equals 3, or x equals -3, excuse me, the x coordinate always has to be -3. The y coordinate, since there's nothing there, can be whatever we want it to be. Since there's no y in the equation, I can pick y to be whatever. Still satisfies x equals -3 if we're picking -3 for x. So do 0, -5, and maybe 3, 1. That gives me 0, 1, and then maybe 3, and then -5. Okay. Let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Let's do blue, green, and then gray. So we have -3, 0, and then -3, 1. Because this was a strict greater than, I know I'm going to be using a dashed line. And then I'm going to be shading in to the right because it's a greater than. Notice that because it's a vertical line, I can't talk about shading above or below. It's now left and right. But the big numbers are to the right. So greater than is right. So I have 0, -5, and then 3, 1. This one was a or equal to inequality. So I know it's going to be a solid line. And because it's greater than, we're really talking about shading above. And then my last one, I have 0, 1, and then 3, -5. And again, this is a greater than inequality. Oh, my green one, I'm sorry, that's a less than. Yeeps, right? I'm talking about below. Okay. And then this guy is this one, and that is above. So the place here that we're interested in is all the way to the right of the blue one, is below the green, and above the gray. So we're talking about like this region here. Notice that the blue line didn't really impact anything. right? Mr. Kulik picked a bad example. That's okay. We're going to stop here. So at this point, you guys should be able to do, from the problem set, numbers 1 through 8. So that'll go on to Sunday's problem set. 1 through 8 so far.